don't want you to spend your time relearning that. I just want you to learn the new material. Let's start. So we are in section 15.3. Section 15.3. What is section 15.3? Triple integrals. So let's assume you have a domain in the 3D. So your domain is in 3D. What is a rectangular domain in 3D? A rectangular domain in a 3D is a rectangular prism. Same story as always. You want to do a Riemann sum first. But your domain is a rectangular prism. So what is the little elements in the rectangular prism? What is it? Is it a line segment? Is it a little square? It is a little cube or little cubic prism, basically. So you divide them that way into little cubes or little cubic prisms. And then, so what happens? Again, I want to make sure that we are understanding this part. Because very soon, I'm going to reduce this to an inner integral plus a double integral. Inner integral and a double integral. But I want to make sure that we understand this. Unless the integrand, this is the integrand, we discussed this a little bit last time. Unless the integrand is equal to 1, you always have a function that is basically changing. Oh, it could be a constant also, but I mean, if that's a function that is not a constant. This is changing. So what is happening is that for every one of these little cubes, you have different, what is that called? Density. When I describe density, I try to do mass density. Mass density is the easiest one to understand. So if you have a mass density, if you know the mass density here, what do? I multiply the mass density by, what do I multiply the mass density by? Volume. So I have a little volume here. I take the mass density, I multiply that by the volume. I get what? Little mass. So little mass here, that's a picture. When you're multiplying that by little volume, you get little mass of that. And then the triple integral sums all the little masses. Right? So it's a little different. Instead of thinking a height is in 4 dimensions, I'm thinking about the little mass and then adding it up. Fair game? So that's the story. You saw that I wrote down the triple integral, the triple sum last time with the limit, which is a weird thing. So I'm not going to do it again. One time is good enough. Now, I want to remind you a few things. First of all, triple integral. If the mass is 1, if I multiply, integrand is 1, and I'm computing the triple integral. That's the notation, by the way. Because it's triple integral, you have the volume element and triple integral. Because of what? Because you have the little tiny cube in there. And if the density is 1, if the integrand is 1, I'm just multiplying volume by 1 and adding it all up. So I end up with what? Volume of W. W is the region in 3D. W is in R3. Right? So that's the first thing that we want to discuss. Then obviously I want to discuss the same thing as we did before. Average of F is going to be the triple integral of F divided by triple integral of the volume of W, as usual. The other thing is the one that I always say to you. When you're computing sigma dVW, density of stuff can be mass if you're confused. This is going to tell you the total stuff. Stuff here can be mass. I have to, because it's not always mass. That's why I'm saying. So I say stuff. Fair game?
What do you mean by F average?
Oh, F average. So in this volume, let's say it's temperature, it's mass, right? Different points, you have different mass or temperature, right? Then I want to know what's the average temperature or average mass density over here. So what I do is basically I compute the entire triple integral over the density and I divide by the volume. That's what's happening. It was before we did the integral of the function divided by the length. Then in double integral, we did the integral of the over the region in R2 divided by the area. Now we're doing it divided by volume. This is again useful. Not only triple integral is not only useful for engineering, because sometimes things are, mass is different and you compute. Let's say some solid is hotter somewhere. Mass is it could be solid or it could be liquid also with a grain of salt. But the density could be different in different places. If I want to find a total, that's what I do. It actually is useful for charge density. Charge density can be different in different places. You want to add them up and find the average. But also it's important, super important when you're doing the actual 526, Math 1 526, which is the statistics using calculus. When you're doing statistics using calculus, that's how you find the average for continuous distribution. Continuous, not discrete distributions. Well, can anybody give me the most famous continuous distribution of all? Who's the fairest of all? Two of them, actually. Does anybody know any distribution? Gaussian distribution is continuous. There's another one that is very famous. Starts with U. You can say uniform distribution. Also, you can use it uniformly. Fair game? Both of them you have to end up integrating. So those are the stories. Those are the fairest of all. So now, obviously, do I want to do Riemann sum? No. What do I want to do? Iterated. How do we write iterated? Why am I not able to do it? Iterated. Integrals. So, for example, on region A, B, cross C, D, do you guys know what this region looks like? It's a cube. In X direction, A and B, on Y is C and D, this one is Z. It's a cube. If I want to find the integral of continuous function F, then it would be A to B of F dx, C to D dy, then dz R to S. Now, you can tell X matches this, Y matches that, and Z matches those. And then you can do any iteration of this. I wrote one of them. There are multiple iterations of this. Any iteration is the same value. Start with an example. Are we ready? Let's do one example. Here's an example, and I can't find the function. B is the prism. X, Y, Z squared. Let's write it as an iterated integral. X first or Y first? Which one do you want? X first. X goes with that. Then Y. Y goes with that. Then Z. Z goes with this. So first thing first, where do you guys think I'm going to start? Most inner. So in here you have the inner, you have middle and outer. And sometimes I say most inner, because then the two remaining one have an inner and outer. That's the only reason I say most inner. Because the inner one, after I do the inner one, then I will have a double integral. That's why. So this one is going to be x squared divided by 2yz, x from 0 to 1. Z squared, thank you. Oh, it's the original integrand was z squared. I just don't copy well. So Andrew caught me. So now x squared is because I took the integral. That's the most inner. These two are the same. And then so I end up with 0 to 3, negative 1 to 2. Plug in 1 and you get yz squared divided by 2. And then 0, which goes away. Now I have to do the middle one, which is the inner of the outer two. And so that one again with y gives me y squared divided by 2. I go by 4, z squared, y equal to negative 1, y equal to 2, 0 to 3, dz. And then when I plug in for y equal to 2, I get 4, and then I get 1. So 4 minus 1 is 3, 3/4 of z squared, integral 0 to 3 to dz, and that is z to the 3/4. Am I doing this right? No, I'm not doing it right because then I have to divide by 3. 12, 0 to 3. The 3 and 3 simplify, 4 remains, and 27 divided by 4 is the final answer. Fair game? We're good? So most inner, then the next and next. Everybody okay with that? Could I? Yes, go. What is the question? Well, okay, cancel out which degrees? Hold on. Oh, yeah, I did divide by degree. Yes, 3 and 3 gets rid of. Yes, it would be 1/4 of z from 0 to 3. Okay, so do you guys have any questions about my method, though? No, any complaint that it could have been easier? I can separate the variables. Yes, it was at a. Yeah, actually, look at this. They're all function of x only times function of y only times function of z only. I could have separated from beginning. The same way we did it in double integrals. Fair game? Everybody caught me on that? So I'm saying you could, because these are, you could write it as this. Because they're function of x only, y only. But then you have to match. Because are these multiplied by their function of x only, function of y only, function of z only, multiplied together? All good? Same answer. Every time I did the work, you guys kind of could tell, but you guys go. I have a lot to cover. This should be a quick one. It should. Wait, what are the bounds for z? For z, 6 and 7. For y, 3 and 4. For x, 0 and 1. Which one has those bounds for all of them? Well, let's do this together. What's the bound for y here? So yeah, this match. Why is it not? Y goes from 3 to 4, z goes from 6 to 7, x goes from 0 to 1. So that one's okay. Not equal to. Not equal to. Find the one that doesn't match. Why is that? Wait, x goes from 6 to 7? Can that be true? No. Did everybody catch that? Questions? Should I walk upstairs? No, we're good? Okay. 4, 3, come on, 2. Any questions? You can also ask Michael. 1. I'm trying to no, they're not. We're good, Michael. 0. B, no, it was okay. People just did it a little smart, a little slower. So far, what have I done? What is it? What has the region been? Prisms. Very, very squarish, right? Prisms. Rectangular prism. Now I want to go any simple solid. So what is happening here? Let me draw at least one of them. Don't laugh at me. Now everybody's going to laugh. So let's say this is the domain. And I want to tell you, first of all, what Z simple means. So we went from rectangular to non-rectangular, but I want to start with simple regions, then get to the more complicated. Fair game? Just like double integrals. So start from here. If I can find the region has like little surface down here, let's call it U1 of x and y, and then another little surface above that, let's call it U2 of x and y. And they're all above D. Then so this is elementary, this is elementary. Elementary. 2 elementary surfaces, right? And that's the only one. So I go, when I'm going in Z direction, I go from one elementary surface to another elementary surface. And it doesn't change. Goes from elementary surface to another elementary surface, and it's always the same one. Yes?
You say it doesn't
I mean, there's not another elementary surface here, and maybe this continues, and so when I move my arrow over here, it goes from another elementary surface to another. Yes? So not always like that. So I'll give you at the end of the lesson, I'm going to give you something that is not simple in one direction. And then on the lab, you get one that is very complicated, not simple. But you divide it into simple regions. So I'm starting with simple, talking about simple regions, then moving on. So when I set this up, please repeat after me. The most inner goal goes from surface to surface. To surface. You have to find those surfaces. That's all I want to say. So surface to surface. So I said z simple. What's the variable for the most inner? Z. Goes from u1 of x and y to u2 of x and y. Then this is the fun part. The fun part is that the two outer one is going to be a double integral. Two outer is with one t, right? A double integral. Sits just like a double integral. But how do I set it up? Do you see that d down here? That's basically the what do you call it? The shadow of this shape on xy plane. Shadow of the solid on the xy plane. That's the domain of the solid in xy plane. Shadow, you find a reflection of the solid on xy plane, then you set up a double integral on that reflection. Reflection of solid on xy plane. That's D. And so it would be a double integral over that. That's the two outer one. Setup is going to be exactly like that. Now, let's use a better picture than mine. Although these are actually, they may actually be my pictures, so they're not very good. Okay. So the next thing is that, what about if it's x simple? Then for x simple, you will have a D in here, sitting in here, and two solid elementary surfaces. One is going to be, this is a better picture. X equal to U1 of y and z, x equal to u2 of y and z. Then the setup is going to go from a surface. Do you guys see that the most inner has two variables in it? The most inner has two variables in the bounds. Remember that one. Don't get confused when you see that. dx, and then double integral of that d, dA. dA in this case is going to be y and z. The other one was x and y. And so on and so forth. And then when you have y simple, you're expecting that, right? Y simple, the most inner is with respect to dy. The bounds are functions of x and z. And a double integral on the region. This is going to be x and z. Okay. Those are the basics. Now let's do an example. So basically, what did I ask you to do? What's the first step I asked you to do? Which one is a z simple? One of the things that you can find is as if one of the variables only appears twice. One is the lower bound, one is the upper bound, right? I wish I had covered the picture because this is a nice one to do. There we go. So I'm looking at this, and actually all the variables are appearing twice. One is a lower bound, one is the upper bound. Lower bound for all of them is a plane, and upper bound is a plane as well. Two surfaces. So let's see. If I draw this, it helps me a little better. X, Y, Z, and I can use that first. That's the, you know the x-intercept, y-intercept, z-intercepts are the same. So this plane out here is that x plus y plus z equal to 1, right? And then you have x equal to 0, which is that triangle in the back, another triangle in the back, and another triangle in the back. Fair game so far? We're good? And then, this is what I want to show you first. Take a quick look at this. If I decide this is z simple, in the z direction, think about the z-axis. In the z direction, is there a surface on the bottom in the picture? It's easy to look at this and know right now, but it gets more difficult. So I want you to recognize those surfaces. Can you tell what would be the lower surface? Here, this triangle down there, which is xy plane. Z equal to 0 is the lower surface. What is the upper surface? Yeah, that blue thing is the upper surface. So Z is between 0 and what? Solve for Z. Solving for Z gives me what? 1 minus x minus y. That's the first step. So I figured out the most inner. I can even write it down. dz, and I'm finding volume. Volume is just f is 1. 0 to 1 minus x minus y. Now I have to set up a double integral. How do I set up that double integral? You have to reflect this shape on xy plane. How do I do it if I have GeoGebra? If I have GeoGebra, I kind of look at this shape. Can you tell what's the reflection of this solid on xy plane? What does it look like? D looks like that, right? Can you tell me what this line is? How do I do it? I just plug in z equal to 0 in the plane to find this line. So that is, if I plug in z equal to 0, I get x plus y equal to 1. And then this is just x equal to 0, that's y equal to 0. And that's my region D. So projection of the shape. Can you guys also tell that the projection looks like a triangle even in the picture I drew without the GeoGebra? Can you tell? So now I have to set this up. How do I set up the outer ones? So the outer one, I know that this is also 1, 1. Let's go with, this is x, this is y. Let's go with the upward arrow. Upward arrow means the inner is what? dy. dy goes from what? 0 to, no, there is a curve. 1 minus x. Then you have to have an x when x goes from 0 to 1. And that becomes the entire thing. Okay, question so far. Someone asked me, well, I want to imagine this better. So basically, what you're doing with the most inner let's say this is the region. With the most inner, you're computing the small mass that comes out of the Riemann sum on the D. The mass, not the height. So the small mass becomes the new height. That's another way of thinking about it. If you want to discuss this, this is like philosophical discussion. Come and talk to me. But, I mean, let me teach it first, then talk to me. And so that's important. First, get the lesson, then talk to me. So now, how do I do this? What is the integral here? 1 minus x minus y. And then I have integral from this and that. Very colorful. And so I would get y minus xy minus y squared divided by 2, 0 to 1 minus x. And then outer is still there. And so I get basically 1 minus x times y minus 1 minus x times x plus 1 minus x to power 2 divided by 2, 0 to 1 dx. This is going to end up to be 1 minus x to power 2 divided by 2, 0 to 1 dx, and you get the answer. Fair game? Are we there still? Okay, so the funky problem is, do you guys know the first problem we're doing is always the simplest one possible? I know the answer over here is 1/6 because it's a tetrahedron. The base is 1 times 1 divided by 2. Then tetrahedron, when I compute, is 1/3 of the area of the base times height. So it would be 1/6. Do you remember those formulas? Somewhat, a little bit? Okay. So question, could I have set up the outer one to be x simple? Outer 2. Yeah, I could have done that also. All the 6 methods would have worked here as simple. Okay. So now I want to give you some that are a little bit more complicated, but not too badly. Am I on the right one? As z simple. Okay, z simple. So it's asking me to find f sub x, y, z. One thing I want you to remember, do you see that? Is that a function given to you, or is it just a random arbitrary function? Arbitrary. Can I integrate that? No, don't integrate that. That's all I'm asking. When you see that, it means that I just want you to set up. Set up is important for us. It's most of the work we do here. We do integrate the small amount, but setup is the most important. So in here, I want to set this up, and I look at the functions. I see a y equal to and a y equal to. That could actually work for me as a simple region, but the problem is asking as z simple. So z must be a simple region also. But that is more complicated. Where do you see z in this equation? That's the one, right? That's the only one. So let's solve for z. When I solve for z and I put the square root, am I okay? What did I make an error in? Plus and minus. So it gives me 2 surfaces, basically. The other one wasn't giving me any surface, but that one is giving me 2 surfaces. Now let's draw the picture quickly. It says y equal to x squared plus z squared. Do we remember what shape that is? What is it? It actually tells us. It's a paraboloid. It opens up in the y direction. It gets cut off. Stay with me, stay with me. Cut off at y equal to 4. Ask. No, Noah? No, you good? Okay, so basically that's the shape. Why do I have two surfaces out of that? Top and the bottom. Top and bottom of the same thing. Top above and below the x-axis, xy plane. So it's basically this. The bottom surface is the bottom blue, not the purple. Bottom blue, and the other one, the positive, is the upper blue. The negative is the lower blue, upper blue. Fair game? Okay. So that's the shape, and so I'm going to do, basically, let's set it up. So most inner is going to be going from negative y minus x squared to y minus x squared dz. It said z simple, means z inside. Fair game? Now, what is remaining? So I set up z. What am I supposed to do now? Project this into what? XY plane. What are you guys thinking the projection on XY plane is going to be? What is the thicker part of this? When z is equal to 0, agreed? The thicker part is when z equal to 0. Most inner. And set z equal to 0 in z squared equal to y minus x squared, and you get y equal to x squared. Agreed? So that's one of them, right? But you see that it got cut up at y equal to 4. Agreed? So the shape is, it's going to get cut up. That's x, that's y, and cut off at y equal to 4. I want to go back to, what did I do to it? Did I close it? No, here. This is basically this shape that I'm going to see from the above. Do you see that's that? From above, projected on xy plane, looks like that. Now, the two outer are going to go with this. X simple or Y simple, which one's easier? Both of them are okay. Which one is easier? Y simple in this case. So I'm going to set it up as a Y simple. Y simple means the inner one is with respect to Y. Starts at what, ends at what? No. It's right in this x squared and ends at 4. I scared you, Andrew. So now, who can tell me what is the x running from what to what? So I have to basically go y equal to x squared and y equal to 4 and compute x is equal to plus minus 2. And that's the setup. Question so far. Is everybody imagining these pictures? A little bit? No? We're doing okay? So now you guys are going to ask me, why don't you change the order of this? You ready for changing order? So there are two types that happens. The third one is similar to one of these. Y simple. So let's do Y simple. Where are my pictures? There we go. Now, here is the Y simple. Now, when I'm doing Y simple, I already know what Y is between. Y is between what and what? Okay, honestly, you either have to put test points in here or have to draw the picture. or else I don't know this is the lower, that's the upper. I will give you a picture on the exam. Fair game? So understand this inequality through the pictures. Because then otherwise you have to plug in values to figure out if this is lower or that is lower. I mean, this one is not difficult, but sometimes it is. Fair game? So that's the setting. That tells me y simple inner integral is going from x squared plus z squared to 4 dy. Now, what is the projection of this shape? What are the variables that are missing? What are the variables that are missing? X and z. So x and z, these two outer one are going to be in terms of dA of x and z. Correct? Everybody agrees? So you have to figure out what the x and z projection of this thing look like. Can anybody guess what x and z projection? From that picture, can you guess? What is that? Circle or disk, right? Because it's a region, we say disk. So it is a disk. So what does this disk look like? What's the radius of the disk? How do I figure out the radius of disk? Here you have y equal to x squared plus z squared, y equal to 4. Can you tell now? This disk, that disk comes from where the two of them meet. The two surfaces are meeting. So what is that? So the radius is 2. Fair game? Okay. So x simple or y simple? Or does it matter? Either one. Both of them are nasty. So I did y simple. Z simple. Z for the double integral. Double integral z simple. Because the original integral was the y simple. Now, in the z simple I solve for z, what do I get? Is that correct? Plus and minus. So the lower one is z equal to negative square root of 4 minus x squared. The upper one, z equal to positive 4 minus x squared. Fair game so far? Okay. Now let's set it up. So I'm going to erase this. I just wanted to remind you is dx and d. And put dz first. And negative square root of 4 minus x squared to square root of 4 minus x squared. And then dx, x goes from what to what? Negative 2 to 2. Next week, this is all you're doing, the entire week. What's that? Yes, that's the one that has to be constant. Sometimes these are constant too. Just setting it up. I just want you to improve your 3D picture. Yes, through the 3D picture. Yeah, I know. You're gonna learn it. It's okay. You're gonna learn it. I mean, everybody says, oh, I don't know how to set up 3D. And then at the end of the semester, everybody says, oh, that's easy. But there's a resistance when we start every time. There's a good percentage resistance. So outer has to be, most outer can it have variable in it? No. So, middle one, can middle one have a variable of the most inner? No. Is there a middle one that has a variable of the most inner here? Can we mark that one? Are you guys doing okay? By the way, I haven't even asked today. Everybody's okay? 5 more days to break. 5 more days. It's a longer break. You're Jacob. You're Ian. No, I'm confused. You're Jay. Him. No, Junwa. John B. John B. Can't remember your name at all. Achin?
Yeah.
Achin. And that's Eric and Lucas. Okay, so any questions? We're good? Was it so far okay? Okay, sort of. Lucas. Yeah, because we integrated Z can't be in there anymore. So the most, as you go outward, the inner variable should not show. That's why the most outer is constant, because all of them are out. As you walk outward, guys, please don't hate me. I want to do one more example. 4, 3, 2, 1, 0. C. D. C. Okay. Here's a little problem. I kind of wanted to do non-simple region. I won't get there, but let me start this. This actually can be non-simple in one direction, but simple in the other directions. This is one of them. I just started, then do the non-simple next time. Can I do it in 2 minutes? So here's the picture. Here's the picture. Can you guys tell that there are 2 surfaces for the lower part of, this is, red is x-axis. Can you tell there are 2 surfaces? Yeah. But what about y direction? 2 surfaces or 1? 1 is just the lower and upper part of the 1. And z is only 1 also. So the first part of the problem, let's set it up. I don't remember which one is asking. It's asking you to set up as dz. Let's set up at dz. Which one has z? This one has z, that one has z. So z is between, I can say from the picture, z is between 0 and x, right? So now, what is the projection on xy plane? Projection on xy plane looks like this. Oh, I don't know. What is this shape? Huh? It's just x equal to y squared, right? Because there's no z. If I set the z equal to 0, I still get that. And then I have here that is x equal to 1. So I get, guys, you can yell at me because I wrote the x and y in the wrong direction. It's x equal to y squared. So it looks like this, and then x equal to 1. So I'm going to go with the x direction. Most inner with z. And then here with x going from y squared to 1, then -1 to 1 dy. Okay, so next time I'm going to set this up in the most inner x direction. Don't throw these notes away. I'm doing the non-simple region. That was not as fast as I was going to be.